Well, see, there is one example now we have for this measurement of enthalpy. This is a very simple example I have taken. See, uh, for the reaction A to B carried out under isobaric condition, a temperature change of minus 2.7 degrees Celsius. So you can write here delta T is equal to minus 2.7 degrees Celsius is equal to, you can write minus 2.7 degree Kelvin, right? Or Kelvin. And Cp for this product and calorimeter, it is given this. So this is very simple question. We can solve this. Delta H of the reaction at any specified temperature. See, temperature is not given but not required also here. That is a constant temperature at any temperature at which it is asked, because this delta T is given. So this is equal to what we have, formula minus uh, T1 to T2, T1 to T2. So if you remember the measurement of delta H, what I have explained to you, then you can very easily find out this Cp of this product plus calorimeter into delta T, right? So this we can write here minus T2 minus T1 and delta T already it is given here. So or dt, we can write here dt. So this we can write here minus Cp. Uh, this is given 71.3 joules per Kelvin multiplied by minus 2.7 Kelvin, because it is given delta T is given directly. So this is equal to 192 joules, right? 192 joules. So in this way you can calculate the enthalpy change for any given reaction. If Cp of product or even only for calorimeter is given, then also you can calculate, because most of the in most of the cases what we are designing that this Cp for calorimeter and not for product. So it is very less, or only with respect to calorimeter we can calculate. So depending on the situation, you can very easily calculate. So we have developed the idea about the standard state, what is enthalpy, what is enthalpy change, what is the reference point for this, everything we have calculated, developed the concept. Now I am moving for the calculation of enthalpies for different reactions, thermochemical equations. And on the basis of the specified thermochemical equation, we have different different kinds of enthalpy, right? Depending on the nature of the reaction. But before going into the detail, there is one law called law of Hess, or Hess law. Simply, you can say, which you can use to evaluate the enthalpy for thermochemical equations, right? So Hess law, this is very popular and very simple law. This law states that if we are converting any process in one step or in more than one step, the enthalpy change is always same. So, if you want to calculate the enthalpy change for a desired reaction, so you can make the algebraic summation, basically algebraic combination of different reactions of which data is given, and by algebraic combination involves both addition and subtraction, multiplication, division, everything involve algebraic combination. So by multiplying with any factor, by dividing any factor, by adding, by subtracting, whatsoever reactions are given of which data is available with you, you can manipulate them in algebraic manner. Means what algebra states that if you are reverse the reaction, then sign will change, like that. Everything you have to follow the algebraic rules. So you can calculate the enthalpy change for any reaction. So the law of Hess states that the law of Hess, the law of Hess states that the heat of reaction for a desired equation, the of a heat of reaction for desired for a desired reaction can be calculated by can be calculated by algebraic combination, right? Algebraic combination involves addition, subtraction, multiplication, whatsoever of other thermochemical equations, of other thermochemical equations, correct? And thermochemical equations of which uh, heat of reaction is given, of which heat of reaction is given, right? So basically, the important point is here algebraic combinations. So you can manipulate equation your own way as per the desired equation. So every time whenever you are going to calculate or you are going to solve any question, the first point is you have ability to design the equation as per the question given to you. You are if you are able to design the equation as per the given condition, then the problem is very simple. I mean, students are doing mistake because they are not able to properly frame the equation. This equation, what we have already, I mean, developed the concept in thermodynamics, like isochoric path, isobaric path. Now here in thermochemistry, the path is basically a reaction. If you have designed a wrong reaction, your answer will be wrong, right? So be careful to design the reactions, because here reactions are actually path, right? And you know, enthalpy change or this heat of reaction at constant pressure. This is a state function. So suppose that I am giving you, suppose that a process like A to B, and if you want to calculate delta H for this conversion, but directly no information is given for this, some other information is given, like A to C is given, that here delta H1 is minus X kilojoule per mole. C to some D is given, delta H2, this is Y kilojoules per mole, and D to B is given, delta H3 minus Z kilojoules per mole. So, and if you want to calculate this for the conversion of A to B, but here A to C is given, C to D is given, D to B is given. So, as per this Hess law, you can say, you can calculate this delta H for A to B is equal to delta H for A to C plus delta H for C to D and plus delta H D to B, right? So accordingly you can put the value here, minus X plus Y plus minus Z, so minus Z kilojoules per mole. So as we know that this delta H is a state function, so if it is a state function, means whether this conversion is taking place in one step or in more than one step. Once this B, I mean A to B, means once we get this B as a final state of the system, so enthalpy change is always equal. So this is the concept of this, Hess law. And note one more point here, that all the state functions can be add or subtract in the same manner, but addition or subtraction of every state function, like entropy change, like Gibbs energy change, like internal energy change, is not said to be Hess law, because Hess law states only this enthalpy. But you can make a point here, that note here, we can put a note here, that all thermodynamic state functions, thermodynamic state functions can be calculated in the same manner, same manner as enthalpy, as enthalpy. Means if any interconversion is made in one step directly or in more than one step, entropy change, means delta S also you can evaluate in the same manner, delta G also you can evaluate in the same manner, and delta E also you can evaluate in the same manner for any reaction. For any reaction, right? So if delta G is given for various reactions and you can algebraically manipulate them for desired reaction. So all state functions can be evaluated, can be calculated in the same manner as we are doing this for enthalpy. Okay. So this is basically all about the Hess law. This is very simple law, and very easily you can evaluate different enthalpies. Now, depending on the reactions, nature of reaction, we have different enthalpies. We have different enthalpies, right? Now, see one example I have framed on this concept. So, see. Sulfur one crystalline form of the sulfur, as all of you are knowing, and this is a combustion reaction, O2 gas, and delta H naught. H naught means at 1 bar, you know, this naught means 1 bar and 298 Kelvin. This enthalpy change is given. Monoclinic, when you burn in air, this equation is given. Find delta H reaction for this, means transformation of rhombic sulfur to monoclinic sulfur. You have to find out the enthalpy change for this. So these two, for these two equations, data is given. So manipulate these two equations in such a way that you will get this. And if it is required to multiply the equation with any factor, it is required to divide the equation with any factor, you can multiply and divide, and accordingly delta H also will be multiply and divide, as it is extensive property, right? So how to get this reaction? So if you see, this is suppose that this is equation 1, this is equation 1, and this is equation 2. So algebraic manipulation required. So you want this sulfur monoclinic in the right hand side and this in the left hand side. So if you subtract this equation number 2 from equation number 1, so subtraction of equation 2 from 1. So how to write this? See, left hand side you can put a negative sign, and right hand side. So how to write? Sulfur rhombic plus O2 gas, this is equation 1, minus sulfur monoclinic and minus O2 gas give you sulfur dioxide gas minus sulfur dioxide gas. So this is the resultant equation when you subtract this equation from this. So this is cancel, this is also cancel. So now you have sulfur rhombic to sulfur monoclinic. Now accordingly you can subtract the delta H also. So delta H reaction at 298 Kelvin is equal to this minus this. So minus 296.83 minus 297.16. So this is equal to 0.33 kilojoule, right? 0.33 kilojoule. So this is the answer. So in this way you can calculate the delta H for the desired equation if you have the equations for which data is given. So whatsoever data is given, first you have to design that equation for which you are supposed to calculate the enthalpy change, and after that you should manipulate algebraically the given equations of which data is given and get the answer. So this is very simple. But this is a very simple question. Similarly, you may get some complicated questions as well. But if you know the concept that for which endothermic process is there, for which exothermic process is there, and for which positive, negative, and addition, subtraction, algebraic rules, then it is very easy to you to calculate such type of questions. Okay. Well, see now I will discuss one by one enthalpy of for different reaction. So first I am taking enthalpy of formation. Although in terms of enthalpy of formation, we can explain all the enthalpies, but that path is little bit complicated. So I will discuss as per in your book what is given. So first see enthalpy of formation. So dear students, now you have to focus the definition. If you are weak in your definition, definitely you cannot do your problem. Numerical problem, definitely you will face the problem. So very much focused on the definition. See, the enthalpy of formation, the enthalpy of reaction, or we can say the net heat change. The net heat change, net means at some stage energy may be released, or at one stage energy may be absorbed, right? So the net heat change in the formation of one mole of given compound from its constituent elements in their standard state. So all of you are knowing what is the meaning of standard state. See, the key words in this definition: one mole, this is the key word, constituent elements, this is the key word, and standard state. One should know the meaning of all these terminology. What is the consequence of one mole? Definitely the enthalpy of this formation, delta H formation, this becomes what? Intensive. Because clearly here written one mole, and if any property defined per mole means that is a molar property, so definitely it is intensive. Means whatsoever enthalpy of formation we have for a given compound, that becomes independent of the quantity you have taken for the reaction, right? Whether you are proceeding with 1 mole or 2 mole or 5 mole, that hardly matters. When you convert that quantity for 1 mole, every time you will get the same value, right? So this is the reason why otherwise we cannot make the definition for any such technical terms. Means if you are taking 2 moles of reaction, or if you are multiplying any equation by a factor of 2, enthalpy definitely will change. But that is not the enthalpy of formation, that is the enthalpy of reaction. Enthalpy of formation only you say that when the quantity is 1 mole, means the amount of product which is formed there, that is 1 mole. Formation of 1 mole of given compound. So this is the consequence of this 1 mole, that it makes this enthalpy of formation intensive. Constituent elements, all of you are knowing that every molecule or every compound is made up of element. So you have to suppose that if you have taken example of carbon dioxide, so the in the carbon dioxide molecule, the constituent elements are carbon and oxygen, right? So don't take O2, carbon and oxygen like this. Suppose that if you have taken CH3OH, so constituent elements are carbon, hydrogen and oxygen. So basically this is compound, this is compound, and this is constituent element. Constituent element means if you are talking about the formation of enthalpy of formation of carbon dioxide, then you have to make the carbon dioxide from carbon and oxygen, not from any other source. Means suppose that we are heating this calcium carbonate solid. If you heat this calcium carbonate solid, you are getting calcium oxide solid plus carbon dioxide gas. So this carbon dioxide is formed here. So whatsoever the enthalpy or heat energy is changing here, this enthalpy of this reaction, this you cannot write the enthalpy of formation of carbon dioxide. Why? Because here carbon dioxide is not formed from its constituent element. So this is the meaning of constituent element. 1 mole of given compound from its constituent element means the elements which are present in that molecule, you have to consider the enthalpy of formation from those elements, not from any other compound. Hopefully all of you are clear. So this is the meaning of constituent element and meaning of standard state. If all of you are knowing the standard state is 1 bar pressure. You have to fix this 1 bar pressure and constant temperature, and if it is not given, then it is 298.15 Kelvin, and naturally occurring form of most stable form of the element, right? And naturally occurring most stable form of element. For example, here this constituent element, now again come to this, here this constituent element, suppose that this carbon, so suppose that you are taking the formation of carbon dioxide with carbon and diamond plus O2 gas gives CO2 gas, 1 mole of CO2 gas, and delta H of this reaction is also not equal to the delta H formation of CO2. Why? Because see here carbon is the constituent element naturally occurring, but this is not the most stable form of carbon. So this whatever heat is changing in this reaction, that you cannot say the enthalpy of formation of carbon dioxide, right? So naturally occurring most stable form of element. How to get this naturally occurring most stable form of the element? All of you have NCERT book, a reference book, in which a table is given at the end of your book, and for every element whatsoever in your syllabus, for every element delta H formation is given 0, and for the element, for the allotrope for which this delta H standard is given 0, that is the most stable form, right? So you have a source from which you can get the most stable form. So this is also not a proper reaction for the enthalpy of formation of carbon dioxide. So now when you take naturally occurring most stable form of carbon, then that is carbon graphite. Carbon graphite. This time you have taken carbon graphite, but here in place of O2 you have taken O gas. Suppose that if you have taken O gas and you are getting this carbon dioxide gas, this time also your enthalpy change of this reaction is not equal to the enthalpy of formation of CO2. Why? Because this time this oxygen is not given its most stable form. This time here I have given O. So this is also not the most stable form of oxygen. The most stable form of oxygen is O2. Now, if you design the reaction carbon graphite plus O2 gas gives, suppose that 2C, 2O2 and 2CO2 gas. Suppose that this is given. So this time whatsoever the delta H of reaction is given, that is also not equal to the delta H formation of CO2. Why? Why this time? Because see here 2 moles of carbon dioxide were taken. So dear students, if you have did mistake in designing of the reaction, your enthalpy will change, and that will not be your correct answer, right? So what is the correct equation for this enthalpy of formation of carbon dioxide? The correct equation is carbon graphite plus O2 gas gives CO2 gas, and this time whatsoever the delta H naught of reaction, or because standard conditions we have taken 1 bar, so that is equal to the standard enthalpy of formation of carbon dioxide. This time it is correct. So see, you have to extra careful when you are designing the reaction, right? So I have taken all the aspects which usually students are doing mistake. So reaction designing for the formation, that is very important, and whenever you are writing the definition, you have to include all these key points in your definition, right? So this is the, this is the correct equation for the enthalpy of what formation of carbon dioxide, right? Similarly, one I have given you methyl alcohol. Suppose that methyl alcohol is given, methyl alcohol. So now we have to design the equation for the formation of methyl alcohol, right? So write the equation for the formation of methyl alcohol, right? So first point, define standard state. So or define temperature. First you have to fix the temperature. So temperature, suppose that we have taken 298.15 Kelvin, and pressure that is default 1 bar. So our standard state is this. Now you have to focus that okay, at this temperature and pressure, what is the physical state of this methyl alcohol? That is also very important. So the physical state of methyl alcohol at this temperature and pressure is liquid. So you are going to design the enthalpy of formation for methyl alcohol liquid as per your chosen condition, right? So put here arrow. What the elements are there in this molecule, and you have to strictly here you cannot take more than 1 mole. So this is okay. Now carbon, so you can take carbon graphite. This is the naturally occurring most stable form of the carbon, plus hydrogen. The most stable form of the hydrogen is hydrogen gas, plus oxygen. Most stable form of oxygen is O2 gas, right? And now you are not allowed to put here 2 moles or 3 moles. So balance the equations, 3 and 1 4, 2 hydrogen you can put here, and 1 by 2 O2. So this is the perfect equation for the enthalpy of formation of methyl alcohol. And if you have made any change in this equation, I am not telling that energy will not change, energy will change in that equation also, but that energy is not referred as an enthalpy of formation of the reaction. So whatsoever the energy changing at constant pressure here is equal to the formation of methyl alcohol, right? If you have taken here liquid, then this is not valid, right? Because this is not liquid. This is liquid at this condition. Suppose that gaseous is given, then it is not. So now see what is happening inside this. What one more word, technical word here I have used, net heat change. So if you examine carefully in this whole reaction, if you think, and this kind of thinking is required to understand the chemical reaction, that at 298.15 Kelvin, which is a room temperature, normal room temperature condition, so is it possible that this carbon graphite will react with hydrogen and oxygen at room temperature? The answer is no. If you remember that measurement of enthalpy change, what I have told you, then at first we have taken this reactant at this condition, then we will heat. So when you are heating this reaction mixture, first this carbon graphite will change into carbon gaseous. Although I have skipped here so many steps, Because imagine dear students, focus here. Imagine when you have solid carbon and you are giving heat to the system, what will happen? First, this solid will convert into liquid. Intermolecular, interatomic forces will break. After liquid, this will convert into the gas. And I have written here what? Directly gas. So solid to gas, so we can write here, I am skipping, I am combining two steps here basically. Delta H sublimation means carbon graphite to carbon gas. Sometimes what will happen? Examiner may give you the enthalpy of sublimation as well. So if you are not able to break the complex, this is a complex reaction in different thermodynamic steps, then it is very difficult for you to understand the things. Now this carbon graphite is there. Now this hydrogen will decompose and this will dissociate. HH bond will go. So 4 hydrogen atoms gaseous will form here, and here 1 oxygen atom gaseous will form. So here enthalpy of atomization or dissociation, delta H dissociation involved, and this is 2 times of delta H dissociation of HH bond. Here I mean half mole of delta H dissociation of oxygen, because if this is given per mole. So now they will combine and first they will form what? CH3OH gas. CH3OH gas. So in this step some energy will change. That is not the formation. That is not formation. Still this is not formation. This is something else. Delta H1 gas. Now from this gas, some cooling is there. Now your methyl alcohol is formed. Now you have to bring whole product at this stage. So in this way, you have to cool. The phase transition will take place. So there is some energy change at this step also, and definitely this is what? Negative. This is what? This is also negative. Why? Why this is negative? Because here the bond formation is taking place. Carbon, hydrogen, oxygen, all bond formation, and bond formation is always exothermic. So here some energy is released from the system, here some energy released from the system, here some energy absorbed by the system. So overall the net heat change in all these steps, that is this. That's why in the definition I have written net heat change. Net heat change. So whenever any reaction is given to you, because you know bond formation and bond dissociation always takes place in gaseous phase, right? Bond dissociation, bond dissociation and formation takes place in gaseous state. And in a chemical reaction, you are knowing that old bonds are broken and new bonds are formed. So if you want to understand the thermodynamics, thermochemistry of the reaction, you have to very careful, and you must have ability to analyze what different steps are involving in that process. So visualization of steps is very important to understand this thermochemistry. So hopefully all of you understood what is the enthalpy of formation, what is the meaning of different technical terms used in this definition, and uh, how to design the equation for the formation of any compound, right? Now, see, this is the enthalpy of formation. Basically, this is so general that any kind of thermochemical equation, enthalpy we can calculate in terms of enthalpy of formation. See, suppose that we have a reaction, general reaction A. A could be anything. Suppose that this is solid, B. This is liquid, CC solid plus D and D gas. Any general reaction is given, and if you want to calculate reaction delta H naught of reaction, so this is equal to sigma of delta AI delta H formation, right, of products minus delta H formation of reactants. Right? So this general equation we can use. This is equal to C times of delta H formation of C plus D times of delta H formation of D minus A times of delta H formation of A plus means in A, B, C, D, suppose that this is a compound, any compound, so we can explain the formation, means enthalpy change of this reaction in terms of enthalpy of formation of each product here, right? Each reactant and product here. Now, see, I am taking one example of this. Suppose that it is given calcium carbonate solid gives calcium oxide solid plus carbon dioxide gas at 1 bar and 298.15 Kelvin. You have to find out delta H naught of this reaction, right? Suppose that this is given. Okay, so how to proceed this? If you have the enthalpy of formation of calcium oxide, enthalpy of formation of carbon dioxide, enthalpy of formation of calcium carbonate. See, all of you are knowing that this formation of carbon dioxide, this is carbon graphite plus O2, half O2 gas, and of this is equal to, formation of this is equal to calcium solid plus not half O2, this is O2, and this is half O2 gas, and formation of this is basically calcium solid plus carbon graphite plus 3 by 2 O2 gas, 3 oxygen. And all of you are knowing that under standard state, the enthalpies of all these are 0. This is 0, 0, 0, 0, 0. So, for every compound, the enthalpy of formation, this is the reference state that we have taken in the most stable form. Most stable thermodynamic reference, remember delta H naught and delta G naught, delta E naught all are 0 for the thermodynamic references, right? So it is 0. So whatever the enthalpy of formation of carbon dioxide and whatever the enthalpy of formation of calcium oxide, if from addition of these two, if you subtract this, you will get the enthalpy of this reaction. So enthalpy of any reaction can be explained in terms of enthalpy of formation. That's why I am telling you that this is the master case. Now other reactions are defined in the same manner. So on the basis of this, so for simplicity at your level, we are defining enthalpy of combustion, enthalpy of neutralization, other process, some little bit differences are there. So, but this is more general form, enthalpy of formation, and you can calculate enthalpy of reaction, enthalpy for a given reaction in terms of enthalpy of formation. So enthalpy of this reaction, of this above reaction, reaction is equal to the enthalpy of formation of CaO plus enthalpy of formation of carbon dioxide minus the enthalpy of formation of calcium carbonate. And this data is given in your book. So from a data source, I can take this calcium oxide is minus 635.1, minus 635.1, and carbon dioxide is minus 393.5, minus 393.5, right, minus calcium carbonate is minus 1206.9. And all the units are in kilojoules per mole, right? So if you simplify this, so you get this 178.3 kilojoules per mole, right? So this is the enthalpy change for the decomposition of calcium carbonate under this condition. Under this condition, right? So enthalpy of reactions can be explained in terms of the enthalpy of formation. So enthalpy of reactions can be calculated in terms of enthalpy of formation, right? Because in the formation, enthalpy of formation is always shown from its constituent elements in their naturally occurring most stable form. So, and in the naturally occurring most stable form, the enthalpy change is taken to be 0. So, you can calculate any enthalpy change of any kind of reaction in terms of enthalpy of formation, right? Good. So, hopefully, all of you are clear in this regard. Okay.